Hi, this is Professor Fernandez, and in this video we're going to talk about Module 2 in Lesson 14. We're talking here about planes and tangent planes. First thing I want to do is remind you that way back from Lesson 3 in the course, we had derived the equation of a plane passing through a point with a certain normal vector. There it was. If we want to think now of this plane as a parametric surface, that's the topic of this lesson, we could certainly take as the natural parameters x and y and then solve here for z and then view the surface as being parametrized by x and y. We could do that. But if you see what's going to happen here, there's a c in front of the z. We would have to divide by c to solve for z. So we would be restricting whatever we end up with to non-zero c's and then have to go back and analyze the c equals 0 case separately. There's a different way to look at planes that I wanted to introduce you to now that we've done a lot of the two-variable parametrizations. And here's the way that we can think about it. So suppose that I have a point on the plane. So I'm going to start off with a point here. I'm just going to draw the two-dimensional view of this because it's a little easier to picture what's going on. So suppose that this is my point P that's on my plane. And suppose that these two vectors are non-zero vectors in the plane such that their cross product is non-zero. So remember, the cross product non-zero tells us that the angle between these two vectors is not 0 or pi. So these vectors are not parallel or anti-parallel. So let's just take, for example, A to be in this direction, and let's suppose that B is in this direction. Okay, then what's going to happen? Well, based off this point and these two vectors, I can generate my plane. And you can see that if I just kept going this way, kept going that way, and I kind of closed this in, this would be my plane. So this is another way to generate the equation of a plane without needing to go through what we had done in the Lesson 3 content, which yields this equation. So how do I generate that equation? Well, so if I denote by r sub 0 the vector from the origin to the point P, so I'm now thinking of my point and two vectors as sitting somewhere in space, and I'm denoting r sub 0 as the vector to that point. Then I'm going to start writing out my parametrization, r of u comma v. So it's going to start at r sub 0, and then from there, to get anywhere else on the plane, let's say I want to get over here, well, I can kind of think of it as we were doing with the standard unit vectors I hat and j hat. To get here from the point P on the plane, I can go some multiple of A, let me call that UA, and then I can go some multiple of B, let me call this multiple VB, and then that will get me by my vector addition laws to this point on the plane. So the equation that arises from this view of how we get to points on the plane defined by the P points, A vector and B vector, is this one. So this is our new version of the equation of the plane where, because it's a plane, we're assuming it goes on forever, U and V are any real numbers that we'd like. So u comma v is a point in R2. So in the parametrized view that we've been using in this lesson, you can think of u and v as being anywhere in the uv plane. So you pick a point of uv, and then the parametrization that we just arrived at maps that point to produce a vector in space that has the interpretation that it goes from the origin to some point on our plane. And we don't know what that point is. It'll depend on the vectors A and B and also r sub 0. But this is what I want you to keep in mind. And then as we choose different points mapped by the parametrization to perhaps another vector that yields, whose endpoint is another point on this plane here. So I want to show you how this works out a little bit later when we think more generally about tangent planes. But actually first let me do a very quick example there, numerical example, just to illustrate these concepts. So what if, for example, our point on the plane was 1, 0, 1, and we wanted and we were told that the vectors 1, 1, 1, and 1, negative 1, 2 were on the plane. So it really is as simple, almost as simple, because we have, three things going on, as it was back when we were doing the equations of lines. And you were given a point and the vector that pointed in the direction of the line. In fact, you can see that this is kind of one way to think about this equation of the plane. This part should remind you of r sub 0. Oops, let's use this. R sub 0 plus TV. That was the vector equation of a line that we talked about earlier in the course. So that's kind of what this part of the vector of this form of equation of the plane looks like. And now we've added another parameter and another direction, which should make sense. If this parametrized a line, it looked like that. If we add another direction, another line to parametrize, and we look at all the possible places you could be along this line and along that line over here, then that yields a plane. So going back to this numerical example, this would be my r sub 0, and I have my a, I have my b. So my plane generated by this point and containing these two vectors would just be 1, 0, 1 plus u times 1, 1, 1 plus v times 1, negative 1, 2. We could from here write out the parametric equations of the plane. They would have the form x equals 1 plus u, y equals 0 plus u, and then z equals 1 plus, I've been neglecting this term. So x equals 1 plus u plus v, and then y equals 0 plus u minus v, and then z would be 1 plus u plus 2v, 1 plus u plus 2v. And again, you see that these have a characteristic of looking very much like the equation of a line, plus other stuff that depends on a different parameter. So it's almost like, again, we drew up here, looking at what you get when you have two non-parallel lines in the same plane, and therefore getting around the plane by following different multiples of those lines. So this is just a quick example of this new way of thinking about the plane equation. What I want to do next is then pass on to the tangent plane. So what changes there? Well, so here is this theorem that describes what those changes are. First of all, I'm going to assume that we are dealing with a parametrization that is smooth parametrization. So remember, we talked earlier about what that means. And I'm going to assume that at a particular u0, v0 value, I am at point P on the surface S. Great. Then the tangent plane to S passing through P is the plane that contains the tangent vectors RU and RV and has normal vector RU cross RV. So RU and RV here are partial derivatives of R, the parameterization here, with respect to U and V. You can see that that's going to funnel down to partial derivatives of the component functions with respect to U and V. Okay, and then here is the reason, you remember from the Module 1 video, I talked about how I would return to the second requirement to be a smooth parameterization in a future video. This is when I'm going to return to it, and I'll do that in a minute. But let me just point out here that we're being told that the normal vector of this tangent plane is RU cross RV. So let me scroll back up to that definition where we first introduced these parametric surface concepts. Definition 14.1.1. Notice in this definition that this number 2 here, we call a parameterization smooth if RU and RV are continuous and their cross product is not the zero vector. So now this makes sense. You know, the cross product in the tangent plane setting, when I'm looking at the tangent plane to a parametrized surface, this cross product is the normal vector that helps us write down the equation of that tangent plane. So we don't want the normal vector to be 0. So it's for these reasons partly that we call parameterization smooth if they don't have a 0 normal vector effectively for the tangent plane. We also want RU and RV to be continuous. There's all sorts of technical reasons for this, but long story short, we want to be able to draw and calculate tangent planes to our parametrized surfaces, and think of these as technical requirements that serve these purposes to enable us to do that. So I'm going to scroll back down to this theorem and then talk about how we are going to apply it. So let's look at this quick example. So this example says, consider the parametrized surface defined by these parameters. So we have x equals u. I'll write it down here. So this x equals u. Y equals v. And then z is u squared plus v squared. And I'll talk a little bit more about what this surface looks like in a minute. It says find the equation of the tangent plane to S. Okay. So let me first mention that we can find the equation to this tangent plane given all the information that's in this theorem without having to picture the tangent plane or picture the surface that we're talking about. And I kind of encourage you to try to start doing that so you can move away from the need to visualize some of the things that are happening in this course, because certainly, as we've seen before with triple integrals of three variable functions, sometimes you can't visualize what's going on. That being said, I am still going to help you visualize what's going on to connect this new concept you're learning to stuff you already know. Notice here that because x is u and because y is v, I can write z as x squared plus y squared. So fundamentally, the surface S I'm looking at is a paraboloid that opens upward. So we've seen these types of surfaces before. And then I want to find the equation of the tangent plane to S. I noticed right now that I neglected to tell you at what point. So this is at the point 125. So I'm going to put that back into the lesson notes after the video. So the point 125 is x equals 1, y equals 2, z equals 5. So somewhere on this little bit, sort of outer edge, if you will, of the paraboloid. So I'm expecting to get a tangent plane that looks roughly like that. And how am I going to calculate it? Well, I could, using the fact that I now know that z is x squared plus y squared, and I have a point, I could use my tangent plane equation from what we had talked about earlier in the course. That was a z minus f of ab equals partial in x plus dot 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 partial y plus dot dot dot. I could do that. But I'm not going to do that here because instead I want to get rid of this and view this as a parametrized surface as it's given, and certainly illustrate the new content. So I'm going to do that. So I'm just going to put back in here the point. And I'm going to do that following this theorem so we can get comfortable with it. So what is my parameterization? There it is. So the theorem says that the normal vector of that tangent plane is given by this. So I need to do a few things. I need to calculate partial derivative of r with respect to u. So derivative of u with respect to u is 1. And then the derivative here with respect to u is 0. And then here with respect to u I get 2u. I also have to calculate r sub v. So I go back and I redo all this, but derive with respect to v. Derivative there is 0. Derivative here is 1. And the derivative here is 2v. Great. And then I calculate the cross product, RU cross RV. Remember how this goes in our course? We have the nice way of thinking of it as the determinant of a 3 by 3 matrix. We put in 1, 0, 2u, 0, 1, 2v, and then we calculate this determinant. So I have 0, 2u, 1, 2v in the I hat direction. Alternate the sign 1, 2u, and then 1, 2v in the j hat direction, and then alternate the sign once more, 1, 0, 0, 1 in the k hat direction. Okay, so this gets me, now I do the 2 by 2 determinants. I get 0 here, minus 2u, so minus 2u in the x direction. I get 2v minus 2u, so I get, let's see. Oh, I noticed that I put a 1 here where there should have been a 0. So that 0 should make its way down there. Great. So I get 2v minus 0 with the negative sign makes it minus 2v j hat. And then the last one here I just get 1 minus 0, so I get plus k hat. Okay, so this is my normal vector, and I'm going to just put it in the vector form to make it a little easier to digest. There we go. And that's my normal vector at any combination of u and v along the surface, the parametrized surface S. I'm going back now to the fact that I want to figure out the normal vector at this point. Now this is a point in x, y, and z. So I have to figure out what u and v values this point corresponds to. In this particular problem, that is fairly simple to do because x is u and y is v. In other problems with other parametrizations, this will set up, as it did back with vector equations of lines, a system of equations that you will need to solve to find u and v. For example, what if instead of x being u, x was u minus v, and y was u plus v? Then, because we're interested in this point, we would set x, which is u minus v, equal to 1, because that's the x value, and we would set y, which is u plus v, equal to 2, because that's the y value. And then you see here, I would solve this system for u and v to get the u and v values that correspond to this point that I want to calculate the tangent plane at. But like I said, in this particular problem, u is x and v is y. So I can just look here and say that u is 1 and v is 2. So then I'm going to go over here and write out my normal vector, finally at this point of tangency, as u is 1, v is 2, so I get minus 4, and then this 1 stays. Great, so that's my normal vector. And at this point, I am back to where I was at the first few lessons of the course. I have a normal vector, I have a point, and I'm now going to find the equation of the plane by just using the formulation we had back earlier on in the course. So I have the x component of the normal vector times x minus the x component of the point, plus y component of normal vector, y minus y component of the point, and then z component of the normal vector, z minus z component of the point, equals 0. So that's the equation of my plane. And if I simplify this a little bit just to get something that looks slightly nicer, I get this. So that is my equation of my tangent plane. So if we plotted the tangent plane along with the paraboloid and looked and panned around, this is a picture here on the left is roughly what we would see. So really the new stuff for this module, certainly to do a very quick recap since we're done with the module, to go back up is this new alternative way to think about a plane. We use this old way of thinking about it right now to do this practice problem on the parametric surface, but clearly this is not the only way now to think of a plane. We have this nice alternative where if you're given yet additional information that might be different, if you're given two vectors in the plane and a point on the plane, then we can use this to write out our parametrization of the plane using two parameters, u and v. And then we didn't use this in this theorem because it's more natural to use the earlier plane equation, but if you want to find the tangent plane to a surface, then this theorem tells us the normal vector to that plane is Ru cross Rv. And this is coming from the parametrization of the surface. Again, if you go back to our old tangent plane equation, you can derive that tangent plane equation from this one by parametrizing the surface using the, quote, natural parameters. So if you use the parameter u equals x and v equals y, this is what your parametrization of a surface z equals f of x, y would look like. You can see that if we calculate r sub u, which would be r sub x here, we would get 1, 0, fx. And if we calculate r sub v, we would get 0, 1, fy. So there start appearing the fx and the fy's that are in the tangent plane equation when we first talked about that concept. So you'll explore a little bit of this in this lesson and throughout the practice problems. But anyway, all of this is to say that we now have a fairly general way of finding the tangent plane to a parametrized surface. And because you are free to choose how you parametrize surfaces, therein lies a little bit of the generality. You could do this to parametrize a surface of the form z equals f of xy, and that will get you back to the tangent plane equation we already know. You could do other things. You could parametrize surfaces in many, many different ways. So what we're learning now is pretty general in its potential scope. Great, so that's it for this module, and I'll see you in the next one.